I welcome I welcome you all to the Spark Research YouTube channel. This is another session of this course, Signal Processing, and in this session we are going to take the contents from fifth of unit, right? So, what are the contents? We will look into the introduction to the IIR filter, comparison in between the FIR and IIR, and we look the how analog IIR filter can be designed, also how to convert the analog to digital filter and bilinear transformation. Right. So before going ahead, let me tell you these contents will be the useful for your GATE 2027, and so if you wanted to prepare for GATE exam, you can refer to these contents, and we'll also look into the some GATE related important questions. Right. Okay, so here is the syllabus for this fifth unit, introduction to IR filters, and so here you can check. And in this session, we are going to actually we are mostly we are going to have the backgrounds. That is, how can we design the analog filter, right? Analog IIR filter. So this is the major purpose, and then lastly we will look into the binary transformation, which is the background to design the digital filter, right? So let's start the session. So question number one is, what is this IIR? So IIR is your infinite impulse response filter, right? So here we will have the infinite number of the impulses response. And what is this impulse response? So impulse response, like here you can see here for this one filter, here how many numbers of impulse response are here? Multiple. Amplitude may be very less as we are moving towards the time, but the numbers are is almost infinity. So that is why this is called the infinite impulse response. Now, how can we design these type of infinite impulse response? So see here, major difference is here the inputs, your outputs will yn, that is yn, will not only depend on the value of the action, that is the present input. So action into b naught, this is definitely apart from this. The feedback is there, right? So check here, z inverse, the feedback along with the magnitude a1, and then again it will add, right? So here this is the impulse response z inverse. So finally your yn will be the direct input, that is present input, that is b naught action here in this way, and so this is your direct input b naught into x1, this quantity, so this one, and apart from that we have the y of n minus 1, so corresponding to this, right? So this is the y of n minus 1 and the magnitude is a1. So yn will be the addition of both, that is the present and plus past. So this is the infinite impulse response. So if it is dependent only on the present, that is the finite impulse response, that is FIR. So in the previous sessions, we have already discussed about the FIR. So in this session, we are going to talk about the IIR, right? So advantage is there, high efficiency, lower order of the sharp transition, analog heritage, Butterworth CYC filter. We will look into all these filter, how to design. Latency is lower, few coefficient than FIR or for the same specification, right? Some disadvantages are also there, like quantization noise is higher and the non-linear phase response is also there, right? And here is the response, that is how can you get. So h of z is nothing, that is your transfer function in the z domain, that is equal to y of z divided by x of z. Y of z is the transfer function. What type of transfer function? Z transfer function of the output, that is y of n. So z transfer function of y of n, that is y of z. This is the z transform, xz is a z transform of the input, so right, and we will get the transfer function. So we are going to use this one. Actually here we are going to talk about the z transform mostly. Why? Because digital filter design means the z transform, digital filter means, right? And so and analog means your Laplace type of the transform. So we will look into that. So here is the summary of your z of h of z, that is equal to y of z by x of z. So you can remember these are the coefficient, right? For IIR transfer function, if condition is that yn is equal to b naught x1 plus b1 xn minus 1 and dot 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 like that. So if you are the delaying by the some amount, you can find out the correspondingly the transfer function, IIR transfer function, that is infinite impulse response transfer function, right? And this is the one of the very important equation. Okay, so again, I'm repeating the same equations only so that you can understand. So let's take one example. So in this example, what is the question? Question is that IIR filter is given here. Now what to determine? You have to determine the transfer function, that is h of z, non-zero coefficient and impulse response, right? So h of z you have to find. So here is your h of z. What is the meaning of h of z? That is the output divided by input. That is the yz divided by x of z. So here y of n, that is in the time domain it is given. N is the discrete time. So time domain is given, xn is there and yn and delay in the y, right? So first you can get the values of the y of z, that is y of z divided by x of z. And how will you get? Just you can transfer y of n into the z domain, that is the z transform, right? So and also you can separate your x of n and x of n together, and y of n you can take left side, and then you can write the value of the z transform y h of z, that is equal to y of z divided by x of z. You will get this value, right? Also identify the non-zero coefficient and denominator coefficient, that is the values of the b0 and b1 and a1. All these you can, like, you can correlate to each other, this one and this one, right? And so what is the b0? So b0 is nothing, 0.2. What is b1? Z b1 is 0.4. How? Because z inverse is the coefficient with the b1. Similarly you can find all those, right? After finding, you can hz, you can convert into h of n, and so you can get the h of n. So here you can check the impulse response as an infinite numbers of the terms, where the several terms are calculated as. So here you can calculate h of 1, put the value of n is equal to 0, 1, 2, 3, 4, and you can find the values of h of 0, h of 1, h of 2, h of 3, and infinite response will be there, right? So h, maybe h of the 1000 you can find out from this equation. So this is the one of the example of the infinite impulse response, right? So here is the comparison between the FIR and the IIR filter. So FIR filter means depends on the present inputs, and IIR filter means depends on the present as well as past also, right? So DAPS is here only depend on the input signal. So here it will depend on the input and past both. Always stable. FIR filter will be always stable, but IIR may be stable, may be unstable, right? It depends. So you have to check the poles, whether is it inside the circle, unit circle, or outside. If it is inside only, then it will be stable, right? So FIR filters, impulse response, no feedback, complexity is lesser, always stable. So and for IIR filter, it has the feedback, then the lower order, and maybe the unstable, like depend on the situation. Okay, so these are the major difference. So IIR filter output y depends not only on the current input but the past inputs, that is x of n minus 1, right? But also on the past outputs, that is y of n minus 1, and its transfer function is the ratio of the numerator polynomial over the denominator polynomial, and its impulse response has an infinite number of terms. Since the transfer function has the denominator polynomial, the poles of IR filter must be inside the unit circle. This is the one of the important always, right? So we will check in the Z plane. Then compare with the IIR. IIR filter offers a much smaller filter size, right? So here now we are going to design the analog filter using the low pass prototype. So this is the one of the very important which can be used for general purpose. So very important prototype, right? So this is the how will you design the first order low pass prototype. So h of p of s is equal to 1 over s plus 1. This is for first order only, right? Not for higher order, only valid for first order. Okay, its frequency response you can find out, like at s is equal to jv you can put, and you will get the frequency response of this first order low pass prototype, right? And magnitude you can get from here only 1 over square root of 1 plus v square, right? And so analog low pass prototype transformation into the low pass filter. So here is your prototype and here is your actual low pass filter. So how will you get the low pass filter? If you are substituting the value s is equal to s by omega c. So here this is your s, and replace your s is equal to s by omega c in order to get the low pass filter. So this is the one of the example, right? So this is the most important. This is the prototype, and here if you will put s is equal to s by omega c, then you will get the low pass filter. So this is the what prototype, and this is the your filter design that you want to design, right? As for example, how will you design it? So here we are going to replace this s is equal to uh, s by omega c, and here is the prototype, right? So put the values 1 over s, the instead of s by omega c, and solve it. You will get this transfer function. So this is nothing. This is the low pass filter, and magnitude you can calculate like this, right? Similarly, you can calculate the phase. Similarly, if you will replace the value of s by the different terms, you will get the high pass, band pass, and band stop, all these. So this is the one of the important one. If you will remember these prototype, it will be very easy to design the any type of filter. So this is the most important prototype. Okay, so let's see here how to replace the value. So here if you replace the s is equal to omega c by s, then we can convert into the high pass filter, right? Similarly, if we'll convert s, the use s is equal to s square plus omega naught square divided by s omega, you will get the band pass filter. And the same prototype use and replace the s is equal to this quantity, you will get the band stop filter, right? So nothing is there. Just check the previous slide, the 1 over s plus 1, and we'll change the values of the s, replace, and get the different type of the filter. So this is high pass filter, band pass, and band stop type of the filter. Why all are these called the different type of filters? So here gain is very high, that is why this is in this region, so greater than omega c, that is why this is high pass filter. And gain is high only in between the particular range omega 1 to omega h, so this is the band pass, so it will pass these frequencies only. Here it will stop these frequencies, and it will pass these, because gain is higher for this frequency, so this is called band stop type of the filter. Okay, so now let's take the some question based on this. So HPS is equal to given your first order only, right? First order prototype function, that is low pass prototype, that is 1 over s plus 1, very well known, and this is very important. So now what to do? You have to determine each of the following analog filter and plot their magnitude, right? So high pass filter with the cutoff frequency of this, and band pass filter, right? So how will you do? Already you know how to design the high pass filter, band pass filter. Just check the previous slide if you have any confusion. So here we are going to we are going to replace s is equal to 40 by s. Omega is your 40. It is already given in the question, right? So put that and replace and get the value of h of s. So here is the summary actually. So like here h of s you can get 1 over s square plus 100 divided by 20. So then if we substitute these values into the low pass in order to get the value of the band pass filter. So why are we substituting this s is equal to s square plus omega square divided by 20s? So you can check in the previous slide, right? We have already discussed, and also you can check it here. Here is the summary. So in order to get the value of low pass in this here now prototype is there. Here what to do? Replace the value s is equal to s by omega c. For high pass, replace omega c by s, same equation. So this is the prototype, right? And for band pass, here you have to replace s square plus omega naught square divided by s omega. Similarly for band stop, so replace all these values in order to get the band pass filter, high pass filter, whatever the types of the filter you want to design. So this is the one of the important. But remember, this is valid only for first order, right? So for higher order, you have to use another type of the prototype type of the equation. So we are right now we are talking about the first order only. Okay, let's take some more questions. Okay, so let's go ahead. So here is the bilinear transformation and frequency carrying. Now question is that what is this bilinear transformation? And so here binary, actually why are we using? So if you remember, the Laplace transform is primarily in the analog domain, but Z transform, whenever we are talking about the Z transform, that is nothing, that is the the your digital. So here, in order to convert the analog to digital filter, we are using this bilinear transformation, that is Z transformation, bilinear Z transformation, right? So here is the analog type of filter that you might see here, and here is the digital type of filter. And how we'll do? So Z, that is, we are going to replace is equal to Z is equal to 1 plus ST by 2 and divided by 1 minus ST by 2. So this is the one of the very important results. You can remember it, and we will look into that why are we using this equation only in order to convert the linear analog to digital filter. Okay, so let's see. So bilinear transformation and the frequency warping. So whenever we are changing from analog to digital, no, again frequency need to be warped. So the area under the curve can be determined using the which type of equation? This 0 to t. This is very general one, 0 to t and xt dt. Here suppose your xt is this function and your time axis, and so yt will be the, suppose, the area. So integration, like how will you get the area? Just integrate it over 0 to t and xt dt, so that you will get the area, right? So just how can we take the Laplace transform? So if you are, in order to get the Laplace transform of this function only, yt is equal to xt xt, so you will get this type of equation here after taking the Laplace transform. So yt will convert into the ys and xt will convert into the x of s, and since integration is there now, so that is why this will be x of s by s as per property, Laplace transform property. You can check it, right? Further you can convert this one, gs is equal to, your gs means your transfer function only, output divided by input. So here ys divided by x of s, that is nothing, that is 1 by s, right? And now let's find out the inputs. This is the transfer function in the analog format, right? So analog. Now we'll do it in the digital format. So y of n, you can write y of n minus 1 from here, check it, and then plus x of n, the difference of this x of n plus x of n minus 2, and take the average divided by 2 and into t. So this will be the y of n. Now convert this y of n into the y of z. So here you can convert z inverse y of z, and t by 2 is as usual xz and z inverse. So we are converting into the z transform, and then you can further find out the the z of transform, z transform. From here you can get the z transform, so that will be equal to y by x, right? So you will get this z transform. Now once we will get the z transform, then what to do here? Now here is the analog one, analog filter, analog one, the output. So you can compare the this one and this. So analog and digital both should be same, because the our objective is same. So then you can get the relation in between s and z. So this is the value of s from same equation, and this is the value of z. So with the help of this equation, if you have the values of the s, then you can get the value of the z transform corresponding to that particular s. So this is the one of the very important results, right? So that we have discussed in the previous slide. So very important. So we will use these to convert from the analog to digital. Means if you have the value of s, put the value of s and convert it to the digital, that is the z. So this is very important one. So let's see here. So left half of the S plane is mapped into the inside of the unit circle of the Z plane, right? So this one we are, this is in the S domain, that is Laplace S domain, contain analog domain, and this is the Z transform in the left, in the discrete domain. So this left one will be, the merge here, and similarly the right half of the S plane mapped outside. So here it will be outside of the unit circle, right? So positively, for the positively JV axis portion in the x plane is mapped onto the positive half circle, right? And the lower one will be, the merged, the mapped into the lower half circle. Okay. Here is the one example. So assuming t is equal to 2 seconds and your suppose the given the following points, you have to find s is equal to minus 1 plus j on the left side of this. So how will you bring into the z domain? So in order to do so, what I told you, like you have to remember this is the primary equation which is being used to the convert your analog to digital, that is into the z domain. So put the values, whatever the values of s is given, just put it here and you can convert it to the z domain. So put the values from here only. From this equation only you can find out z is equal to 1 plus here s, instead of the s we are going to use, right? So put the value and get the value in the z, that is in the z transform. Similarly for two number, put s is equal to 1 minus j and get the value of z. Similarly for 3, z s is equal to j, put the value and get the z. So this is the how will you convert, right? So this is the conversion from the S plane to the Z plane. Very easy conversion. Some more question you can check here. Here given analog filter whose transfer function is given, and you have to convert it into the digital filter. So how will you convert if sampling period T is given? So bilinear, we are going to use the BLT transform. So here h of z is equal to h of s, and that is s 10 divided by s plus 10 here already given, and we have to use again in order to convert your analog to digital, that is s2z, that is s is equal to your twice of z minus 1 and tz minus plus 1. So same equations we are going to use. Put the values and get h of z, and then you can get the inverse z transform, you will get the y of n, right? And once you will get the y of n, then further you can substitute s is equal to j omega a, and then z is equal to e to the power j omega dt, and get the value of j omega a. So this will you in this manner you will get the value of omega a. Omega a is the analog of frequency is marked on the j omega axis on the x plane, and omega d is actually the digital frequency, right? So omega a is your analog frequency and omega d here, that is your digital frequency, right? So here is the plane, as plane you can the mapped into the z plane with the help of these equations, right? So IIR filter design, so bilinear transformation and frequency warping. So here you can see the some more detail about the same. So S is equal to, just remember 2 by t z minus 1 divided by z plus 1. This is the one of the most important. Here is the summary actually. This is the S plane and here is the Z plane. So S plane left side you are going to the map inside the Z plane, and this is the equation that we are using, that is a transfer function in the Z transform, right? So here how will you work the frequency here? So omega will be twice of arc 10 and omega t by 2. This is also the one of the important. So here low pass filter you are going to wrap at omega 1, and high pass filter you are going to wrap and the band pass filter, right? So some more examples we will look. So low pass filter, here we are going to use omega A is equal to twice by 10 of omega D by 2. Similarly for band pass and band stop filter, these are the values, right? And what are these? So omega AL, omega AH. So you can check here for low pass filter HPS. So this is the, we are always using the same prototype, that is for 1 over s plus 1, that is for the first order. So replace all these values in order to get the value of the filter, right? So here the steps, how will you get? So first analog filter is there, analog low pass filter, that is, and then replace it as is equal to s by omega a, and you will get the analog low pass filter specification, and then replace the value by linear transformation, that is s is equal to 2 by 2 z minus 1 divided by z plus 1 in order to convert the digital low pass filter, right? And then further the final step is your omega of a, you can and get these values, replace and get the value of the filter, right? So step one is a prototype, step second is the replace the value, step third converting into the the digital, and final step is to get the design of the filter. Okay, so some questions you can check since session is the bit longer, so I'm going quickly. So here you have to design normalized low pass filter which HPSC is given first order only, and then find out step 1 2 3 here. See, first step, so you have to calculate the pre-warped analog frequency using this equation, find out, and then h of s you can replace the value of s is equal to, so that you can get the for the prototype transformation, then BLT you can apply, and then you can get the value of the h of z. Finally you can convert back into the the values, and you can simplify and you will get the value of h of z, that is transformation. Okay, so you can check these the solutions in more detail. Thank you to sign this.